I am Janne Kokkala. This is joint work with Jakob Nordstrom, who leads the Meow research group in University of Copenhagen and Lund University. So here is an example instance of the SAT problem. We have a Boolean expression in the CNF form where we have a bunch of clauses, and the question is whether we can assign values to the variables so that each clause is satisfied. The problem is NP-complete, and this formulation might sound a bit unnatural, but it actually is often a useful approach because so-called conflict-driven clause learning solvers are just amazingly fast in many real-life instances. The idea behind the dominant CDCL paradigm is that the solver derives or learns new clauses until it finds a satisfying assignment or reaches a contradiction. And one great feature of many CDCL solvers is that in case of negative result, these learned clauses actually give a proof of unsatisfiability, which can then be used to verify the result. So why are CDCL solvers so good then? The state-of-the-art solvers use many fine-tuned heuristics which are crucial for performance. Some of these important heuristics are, for example, how to manage the clause database, as keeping too many clauses in memory would slow down the solver too much. Also, it seems that to perform well, the solver needs to restart the search every now and then. One possible way is to just go with a fine-tuned static restart schedule where the search restarts at predetermined points of time. And another approach is to use adaptive restarts where the solver restarts when it seems to be producing bad clauses. So in state-of-the-art solvers, these heuristics do work well in practice, but there is surprisingly little rigorous scientific understanding of why they work. Why are certain heuristics so good? In this work, we seek some understanding by looking at the proof of unsatisfiability to determine what part of the work the solver does actually contributes to the proof. So what do we learn? First, if we were able to keep more clauses in memory, it would help the solver focus the search on the proof, but it would not actually make the actual proof shorter. For a static restart schedule, more frequent restarts seem to actually improve the reasoning power of the solver, which means that the proofs also do get shorter. And from these proofs, we find evidence that adaptive restarts indeed help the solver avoid useless work. Some of the main heuristics that solvers use to determine which clauses to keep in memory are LBD, which is kind of a locality measure, and activity, which measures how much the solver uses the clause. And we find evidence that these are indeed good predictors of whether the clause contributes to the proof. So let's now see in a bit more detail how CDCL solvers work. Here is an example of a full solver run on this formula. Unfortunately, I don't have time to go through this example in detail. The full example is in the paper, but some main points are enough for this presentation. So first, the solver makes a decision, that is, assigns some variable to a value according to some heuristics. In this case, we set W to false. Then, if any clause with the current assignment implies a value for one literal, then that assignment is added. This is called unit propagation. So in this case, the clause not U or W and the assignment W is false imply that U has to be 0. So U propagates to 0. Then the solver continues with decisions and unit propagations. And finally, if unit propagations lead to a conflict, the solver uses the reasons of unit propagations and the conflict to derive a new clause that is sort of a reason or explanation for the conflict. And this is actually equivalent to a no-good in constraint programming language, which you might be more familiar with. Then this procedure is repeated until a satisfying assignment is found, or in this case, the solver learns the empty clause, which means that the formula is unsatisfiable. And actually, if we look at how all these learned clauses were derived and used later, we get a graph like this. And this graph actually corresponds to a proof of unsatisfiability of this formula in the resolution proof system. And because CDCL solvers work or provide these proofs always, it's often insightful to consider them as engines that search proofs for unsatisfiable instances, which is also what we do in this work. So let's now spend a moment to see what this graph means and what we can observe about the solver. So first, all clauses with no incoming edges are the formula clauses. And then new clauses are derived from these. And finally, the empty clause. But in this work, the interesting new clauses are the ones that the solver stores in memory to use later, the no-goods called learned clauses in the CDCL language. The remaining clauses are intermediate clauses used in the conflict analysis but not stored permanently. In particular, we are interested in the question what clauses are needed to derive each new learned clause. So let's give some examples. If we take this learned clause, then these two clauses were used to derive it. For the next learned clause, these three clauses were used to derive it. And so on until the empty clause is learned using these four clauses. Okay, then we can ask what part of the derivation and which clause usages were actually useful for reaching the result. Well, obviously the empty clause is of course needed because it is kind of the final result. Then all clauses that were used to derive this are also considered useful. And all clauses used to derive them, and so on, and so on. Now we can notice that the first learned clause does not actually take any part in the proof. The solver did learn it, but it was not required for the actual resolution proof. So we could get a smaller resolution proof if we only consider this useful part of the derivation and we can call the remaining part sort of useless work. So in this work, we are interested in whether the solver is doing useful or useless work, and we sort of use this resolution proof idea to approximate what part of the work is actually useful or useless. Of course, in practice, the clauses are useful in other ways too, but this is sort of like a first approximation to see how the solver is deriving these proofs of unsatisfiability and what helps the solver do that. A similar approach of looking at proofs has been used in a few earlier works. For example, Simon in 2014 performed a thorough analysis using the glucose solver, asking questions, for example, how much the proofs change if we shuffle the instances, the formulas, how old the clauses that are used are, and which features can predict useful clauses, and then comparison of some solver heuristics and how they affect the proof. In another work, Katsirelos et al. Studied the structure of proofs and studied what they can tell about barriers for parallel set solving and clause sharing for parallel set solvers. And Simon and Audemars devised a strategy for clause sharing based on some observation related to that work and how clauses are used. Recently, Sauce et al. Used machine learning techniques to try to predict clause usefulness during the solver run. And finally, there's interesting work done by Malik and Ying, who, instead of looking at simply clauses in proofs, also considered a similar notion for event dependency graphs, which means that in addition to only clauses, they also divided decisions and propagations into useful and useless work or events. So to get back to our work, we have two main questions here. First, we want to understand how different heuristics affect the solver reasoning or the solver performance, and for this we compare the proofs produced by different solver configurations. In the other part, we look at the used clauses and useful and useless clauses in more detail to see which features can predict whether a clause will be useful. As mentioned earlier, we divide the work done by the solver into useful and useless work. We call the proof containing all derivations, both useful and useless, the untrimmed proof, and the smaller proof containing only the useful derivations, the trimmed proof. For experiments, we run a modified glucose 3 on a sample of randomly chosen unsatisfiable instances from recent set competitions. And here I need to emphasize that all our experiments are indeed done only on unsatisfiable instances, so it's a bit unclear whether these observations apply for satisfiable instances too. But for unsatisfiable instances we can learn something. So let's go to the results. First, consider the clause database size and clause database management. So we know that keeping too many clauses would slow down the solver way too much, because it would need to spend time checking these clauses for propagation and so on and so on. So clauses need to be erased regularly. But the question is, like, do we lose some reasoning power by not keeping all clauses? And so we see that if clause erasures are switched completely off, then it seems that the solver can focus better. What I mean is that it seems that the trimmed proof size does not change, so the solver seems to be finding a similar proof, but the untrimmed proofs get clearly smaller, which indicates that there is much less wasted work by the solver. So for static starts, we know that tuning the frequency is very important. So tuning or using too frequent or too infrequent restarts slow down the solver too much. But then another question is, like, how does this affect the solver reasoning, and why do restart frequencies behave this way? So it seems that for most reasonable restart frequencies, more frequent restarts do give shorter proofs, which means that the reasoning power of the solver is actually improved by restarting more frequently. However, if we go to very, very frequent restarts, such as restarting after every conflict, then the results are more unclear. So actually, even if we don't care about time, still restarting at every conflict would not be the best possible performing solver in terms of reasoning power. So for adaptive restarts, we know that adaptive restart policies work in practice much better and much faster than static restarts. But we want to also ask the question, like, why do they work so well? What is their effect on the solver reasoning? And we find that adaptive restarts indeed seem to work by cutting away unnecessary search, just as the intention is. So the trimmed proof sizes remain the same, so it seems that the solver seems to find the same proof, but then the untrimmed proofs get smaller, which means that the solver does much less work. So it seems that adaptive restarts cut away like useless work. Then one might wonder whether the adaptiveness is just about like tuning the restart frequency for each particular instance. But actually, if we for each instance use a similar restart frequency for static restarts, which the adaptive restart method finds, the adaptive restarts are still much better. So it seems that adaptive restarts are doing a good job because of the timing of the restarts. So they indeed can detect if the solver is doing useless work, at least to some extent, of course. So we know that it's important to erase clauses from the database regularly, but the question is, how do we decide which clauses to erase and which to keep? Common heuristics include keeping track of an activity score for participating in conflicts, which is one of the first proposed heuristics. But nowadays a more commonly used one is literal block distance, LBD, which is sort of a locality measure of the clause, which takes into account the current part of the search tree where the solver is at. And actually in 2016, Janne suggested that we should choose the very best clauses by their LBD score, but then for the remaining clauses we use activity score to decide between them. And this also seems to be working well in practice. And it turns out that our work does support this idea. So very good LBD scores indicate a useful clause, but activity can predict over like a wider range of clauses. So a combination of them seems like a good approach. And curiously, very, very high activity scores seem to be bad. So they seem to indicate useless clauses. So maybe the solver gets somehow stuck on using some clauses, and then it turns out that these are not useful anymore. So to summarize our work, the motivation was to understand why CDCL chat solvers are so good in practice and why the heuristics work so well. As said, there is very little rigorous understanding of like possible theoretical reasons behind these heuristics, but we know that they are good in practice. So our approach to tackle this question was to analyze the proofs that the solvers produce. And with this approach, we managed to shed some light on how different restart policies and closed database management policies affect like the internal workings of the solver and not just the runtime performance. Of course, this work merely scratches the surface, and there's a lot of interesting questions to be answered in future work. For example, as I mentioned earlier, the big caveat of this work is that we only considered unsatisfiable instances, but it could be that for satisfied instances, the heuristics somehow perform very differently. But one could or one can think of a similar notion of like a derivation of a satisfying assignment and use that to study it. So we somehow isolate clauses that were useful in reaching the satisfying assignment. Another interesting approach would be to study the actual properties of the proofs and relating them with what we know from proof complexity. So for various crafted combinatorial formulas, there are many known theoretical properties, and it would be interesting to see whether these theoretical properties of the proofs are visible in the actual proofs that the solvers find. And finally, we were able to study only a couple of heuristics and fairly traditional techniques, but the CDCL world is evolving all the time, so it would be interesting to apply the same method for the newer techniques also. So thank you for listening, and I'm looking forward to meeting you at the Q&A session.